Hello, am I audible?
Yes, sir.
Okay. So, hello everyone. I am Vanshu Mishra, and for this week we will be solving some problems related to radiation heat transfer, basically radiation exchange between different surfaces. So last week we solved some problems related to boiling and radiation heat transfer. This week we will wrap it up the radiation heat transfer, and from the next week, I guess we will start with the heat exchanger problems. So let's start with the first question. So in the first question, there is a furnace cavity which is in the form of cylinder of 75 mm diameter and 150 mm length. Is open at one end to the large surrounding that are at 27 degrees Celsius. The sides and bottom may be approximated as black bodies are heated electrically, are well insulated and are maintained at temperature 1350, 1650 respectively, and we need to find the total heat transfer required to maintain the furnace condition. So here we have a furnace of length L, which is 0.15 meter, and diameter is 0.075 meter. So this surface is 1, and the area of surface 1 is, let's say, A1, and this is surface 2, and this is the open surface. So let's consider this surface 3. So we have a surrounding temperature of 300 Kelvin, and T1 is 1350 degrees Celsius, and the temperature at T2 is 1650 degrees Celsius. And there will be a heat transfer from the walls of this furnace because these are electrically heated to the surroundings. So here the interior surface or the black body surface. So my total heat transfer will be heat transfer from surface 1 to 3 and heat transfer from surface 2 to 3. So the radiation heat transfer can be written as so this is my Q13 and this is my Q23. That means from surface 2 to 3, and F13 and F23 are my shape factor. So let me check. There is a table. So this shape factor F23 can be obtained from the table. That means if you look table in the heat transfer book, so this is my surface I and this is my surface J, and the shape factor for surface Ij will be the function of, this is my x, so this is my x, this is my y, and my height is represented by L. And this is my scaled x and scaled y. So there is a big formula. If you look into the table, let's say table 13.2 in Frank and Corpora. So there is a table which defines the shape factor where we have, when we have given a two parallel surface. So these two parallel surfaces are given in the Cartesian coordinates, and for that there is a long formula which is a logarithm which varies as log and tan inverse, and this log and tan inverse are the function of x bar and y bar. So we calculate by using this formula from the table. We can get the shape factor 2, 3. That means from the bottom surface to the imaginary surface 3 as 0.056. So in the table they have also given a shape factor for the two parallel discs and the perpendicular rectangular surface also. So for this they have given some empirical correlation, and then there is a graph. You can also find the shape factor between two surfaces, let's say I and J, by using the graph also. Like for the parallel rectangles in the figure 13.4, in the same book they have given a graph where you can find the shape factor between two parallel planes, and using the same graph you can find the shape factor between two circular discs also. So in case you don't have any idea or input about the shape factor, you can use either this empirical correlation or the graphs. In case you have given some one or two shape factor, or there is a symmetry or some assumption in the problem like symmetry, or you can use reciprocity theorem and so on, then you may use few analytical solution to find the shape factor. In this problem, I am solving the shape factor from the empirical correlation. In the few problems, I will be using the analytical relation, and in the few problems, I may use some graph also. So I will be using the combination of all these things to solve for the shape factor. So we have a shape factor F23 that we can obtain from the empirical correlation. I'm not writing the full because the expression is very big. So we have a F23 from the empirical correlation, and we need to find the shift factor f21. So to find the shift factor f21, we can use the summation rule, which says that the sum of the shift factor equals to 1. So this shift factor f22 will be 0, because whatever the radiation emit from the surface 2 will never receive by the same surface. That means the f22 will be 0 here. And we already found the shift factor f23 by using this empirical correlation that you can find in any book. So here I have given the table location in the Frank and Corbera book. So the shift factor f21 will be 1 minus f23, which is 1 minus 0.056. That means my shift factor f21 will be 0.944. And we need a shift factor which is 1, 3 and 2, 3. So we already have a 2, 3 and we need to find 1, 3 here. Which means from here to here. So we now have shift factor 2, 1, f21. So we can use reciprocity theorem. To find the shift factor f12, because the shift factor f12 will be equal to the shift factor f13. That means whatever the radiation will come out of this surface and incident on surface 2 is equal to the same radiation in the equal amount will incident on surface 3. Which means my shift factor f12 equals to f13 and can be given by this using the reciprocity theorem. Then I can find these shift factors. So my area A2 will be just area of a disc. And my shift factor f21 is this. And my area 1 will be this one. It's a cylinder actually. So this is not a straight line, it will be like this. It will be like this. So it will be pi dl. And my length is 0.15 meter. So my shift factor f12 or f13 will be 0.118. So we have a shift factor f23 which is 0.056, which I get from the empirical correlation, because we don't have any idea about the shift factors. Initially, there's nothing given in the question, and therefore it is better to find either using graph or by using the empirical correlation. Then we have a shift factor f21 we found, which is 0.944, which we get from the summation rule. And the shift factor f12 and f13, which is 0.118, which we found from the symmetry and reciprocity. So these are our shape factors, and we need to use F13 and F23, which means yeah, sorry. Which means this one and this one. So we just plug the shape factor in the heat transfer equation. And plugging the all other values as well. This is my diameter, this is my length, and my shape factor F13 is 0.118, and my Stephen Boltzmann constant is 5.67 10 to the power minus 8 in watt per meter square, Kelvin to the power 4. And my temperature in Kelvin will be 1623. This is my surrounding temperature. And similarly for surface 2-3, this is my cross-sectional area, pi d square by 4, multiply by the shape factor F23, which is 0.056. This is my Stephen Boltzmann law. And my temperature in Kelvin. So this is my total heat transfer equation. This one. And this equation is 1. So basically this is equation 1 in the where all the values are plugged in. So on calculating this, we will get the heat transfer from surface 1 to surface 3, from surface 1 to this surface as 1639 watt, and from the bottom surface 2 to the top imaginary surface 3 will be around 191 watt. So my total heat transfer will be 1830 watt. So this will be my total radiation heat transfer. So just to recap, here we have given a furnace and we have given a 3 sides. So this is my first side, this is my second side, and this is my third side, which is open. And we need to define the total heat transfer. And my total heat transfer will be the sum of from heat transfer from side to the upper surface and from bottom to the upper surface. And we use a radiation heat transfer concept. So we need to find the shape factor first. That means how much amount of radiation is emitted from the specific surface and reaching to the upper surface. So from the side it is F13 and from the bottom it is F23. Now we have not any clue about shape factor. There's nothing given in the question. So we use empirical correlation to obtain shape factor F23, because from the empirical correlation you can obtain easily for the parallel disks or the parallel surfaces or the perpendicular Cartesian surfaces. For these 3 conditions you can obtain the shape factor. So we obtain for parallel surface. We use the empirical correlation for parallel disks to obtain the F23 shape factor. That means from bottom to top. Once we get that, we use different analytical concepts like summation rule, like the summation rule and the reciprocal theorem, symmetry theorem to obtain the other shape factors. Once we get the shape factors, we just use the Stephen Boltzmann law, this heat heat transfer for the radiation process to just find the total heat transfer. So just in order to compare with the previous questions we have solved, it is just finding the heat transfer coefficient first by using the different correlation or different concept depending upon the type and nature of the flow. Once we got the heat transfer coefficient, we use the Newton's law of cooling. Here we use the different theory or different empirical correlation or by using different graphical method to find the shape factor. Once we get the shape factor, we just need to plug in into the Stephen Boltzmann law to find the heat transfer due to radiation. So any question? Any doubt in this?
Actually, sir, this book which you have recommended,
Yes.
I am not having this book, so can you, how I can get this soft copy?
I will put this book in the Google Drive where I used to put my these notes, lecture notes. In that Google Drive, I will put that book as well.
You will put the graph or the
No,
book?
book, entire book.
Okay. That means it will be available with your video.
No, not a video. There is a Google Drive, right, where I used to put these notes, these PDF notes in the Google Drive. In that drive, I will put.
Okay.
If you don't have a link for the Google, it is there in the same PDF, like same Excel sheet where you used to find the link for videos. In the next column, there is a link for a Google Drive also at the bottom. In any case, I will, whenever I upload this video, I will mention the drive link in the caption of this video. So you can also find the link from the YouTube video, this YouTube video.
Okay.
Yeah. So let's move to the next question.
Or can you mail me, sir, this? If I give you, you can give me your mail and you can mail me?
Sure. Can you give me your email ID?
Yeah.
Or you can just type in the chat. I will.
Okay.
Meanwhile, let's move to the next one. So, okay, I received the email ID. Okay, so in this question, we have given a different. So in this question, we have given a different kinds of arrangements, different geometries here, and we need to find all the shape factors here. Basically, shape factor between surface 1 and 2, without using any table or any empirical correlation, without using any graphs as well. So here we will be using different analytical techniques only to find the shape factor. We will be using some assumptions because we need one shape factor. Once we get any one shape factor, we can use different rules like summation rule, reciprocity rule, symmetry rule to find the other shape factor. So to use the analytical techniques, we need at least one shape factor. In the previous question, we did not have even the one shape factor. So we have to begin with using some empirical correlation or the graphs. But here we will be making some proper assumption here to use the analytical techniques. So let's solve the first problem A, part A. So this is a long duct. And here we have a two surface. So this is my surface A1. And this is my surface A2. And this is a long duct. So by inspection, or we are using the assumption that the view factor F12 is 1. That means whatever the radiation emitting from surface 1 will completely fall at the surface 2. There is no back of reversing of the radiation. That means it is not like the radiation emit from the surface 1 fall back to the surface 1. So this is not possible here from the inspection, which means that all the radiation all the radiation are falling at surface 2. That means shape factor F12 equals 1. So now we can use the reciprocity theorem to find the shape factor F21. So we already know this by inspection, which is 1. So my shape factor F21 will be A1 by A2, where F12 is 1. So my A1 is 2 multiply R by L, and my surface area of A2 will be 3 by 4th, because this is a sector, right, of 90 degree. 3 by 4, 2 pi RL, which means it will be 2 by 6 by 4 pi 8 by 6 pi, which is 4 by 3 pi, which is 0.42 something. So this is my shape factor F21, and from the inspection my F12 will be 1. So for this problem my shape factor is this. So here we just use inspection. We just assume that all the radiation coming from surface 1 will not fall on the same surface. That means all the radiation will fall on the surface 2, which means that my shape factor F12 will be 1. Now we need F21, which we can easily use the reciprocity theorem to find the F21. So by reciprocity we got F21, and by inspection we get F12. Now similarly, let's say for problem B.
Sir, actually in this first problem, it is not given that only surface 1 is radiating.
Yeah, so radiation we have nothing given. So basically in the radiation heat transfer, there will be a emission from one specific surface. When it reaches to the other surface, it absorbs some radiation and then it also emits some radiation. So it actually doesn't matter. So we are here assuming that there is a radiation heat transfer from both the surfaces, and we just need to calculate how much amount of radiation received by the each surface, because there are radiation heat transfer from both surfaces, because either there will be emissivity and there will be reflectivity. So here in this question it doesn't matter, because we don't need to find the net rate of heat transfer. We just need to find the amount of radiation which can receive by the each surface. That's it. So the basic assumption is both surfaces are radiating, or the all surfaces in the problems are radiating.
But sir, like you have taken this first surface, and we always take F11 or F22 is 0.
Yeah, so
So that means F12 plus F11 will be 1 and F21 plus F22 will be 1. So then F21 is 1,
No,
but
no,
here
no,
we are getting 0.42.
no, no, no. What you are saying that, so you can use the summation rule in a two ways for the question one. Let's say this is your uh, this is your surface one and this is your surface two. So here you can use summation rule in a two way. First you select surface one, so I'm writing the summation rule for one only. So here f11 plus f12 equals to 1. Now whatever the radiation emitting from surface 1 will not fall back into the same surface, which means this is 0. So you will be left only with f12, which is 1, which is we already uh, said at the beginning. Now again you use the summation rule for surface 2, which is f21 plus f22 equals to 1. Now this is your surface 2. Now here the radiation emitting from the surface 2 can fall at the same surface. The radiation emitting here can fall at the same surface too, which means that this f22 is not equal to 0. Here it is 0, so f12 becomes 0. This will not be 0. So f21 cannot be equal to 1 because the radiation coming from here will fall here. Similarly, the radiation emitting from here will fall here. So the radiation which is emitting from surface 2 fall back on surface 2 also. It will fall back at surface 1 and it will fall back at surface 2 also, which means f22 there is f22 equals to f22 not equal to 0. F22 has some finite magnitude and so does f21. But we cannot use this relation because both relation are unknown. So we use the reciprocity theorem. We just use this relation to find f12, which is 1. Then we use the reciprocity theorem to find the f21. Now we know the f21 is 0.42. Then we can again use the summation rule here to find the f22, which is 1 minus f21, which is 1 minus 0.42, which is roughly equal to about 0.68 something. So this is my f22, which means the radiation coming from surface 2, 68% of the radiation is falling on the same surface and 42% of the radiation falling on the surface 1, which is coming out from the surface 2.
But sir, you have assumed for surface 1 that whatever radiations are emitted by 1 are not falling back on 1. So, but it will not be actually happening because you are having concave surface upwards.
We don't have a concave surface for 1. 1 has only a flat surface. And here you can use the summation rule to prove the same. So you just use the summation rule for surface 1 and you can find that f11 is 0 because it's not a concave surface, it's a flat surface. And that's why whatever the radiation emitted from this flat surface in the normal direction will not fall back. If there is a concave surface, 1 is a concave surface, then f11 also not equal to 0. There should be some non-zero or the finite shape factor between f11. If my geometry is like this, so here this f11 is also not equal to 0 because it's a concave surface. That means whatever the radiation coming out from this surface 1 will fall from the surface 1. So in that case, it can be non-zero, but my surface 1 is flat, which says that it is not falling back at the straight surface. It is not possible to fall back at the straight surface. So using the summation rule at plate 1, you can easily show that your f12 equals to 1. That means all the radiation coming from the surface 1 will fall, 100% of the radiation will fall at surface 2.
Okay, sir.
So let's move to the next part. So in the next part, we have one small sphere and one concentric hemisphere. So there is a hemisphere and one small sphere, and this is my surface 1, which is A1, having a cross-sectional area of A1, and this is surface 2, and let me draw some imaginary surface here, which is 3. This is A3, this is A2, and this sphere is actually placed at the center. So again we use the summation rule at surface 1. And we can easily find that whatever the radiation coming out from surface 1 cannot fall at the same surface, cannot fall back at the surface 1, which means my F11 will be 0. Now this spherical surface is at the center of this, which means what total amount of radiation which is emitting from surface here, let's say the amount of radiation, the total amount of radiation will be emitting from the entire surface 1. The half of the radiation will receive by surface 2, and the remaining half of radiation will receive by surface 3. And this is only because the center of this sphere is placed at the midpoint of this hemispherical surface. And because of this, we use the symmetry relation, that is F12 equal to F13, which means 50% of the radiation will receive by surface 2, and 50% of the radiation will be received by surface 3. And this is only valid for this kind of an arrangement. If you just move the surface 1 upside or downside, then this will be not true. So only for this arrangement, my F12 equals to F13, and this is equal to 0.5. 0.5 because surface 2 will receive 50% from surface 1, and surface 3 will receive another 50% from surface 1. So my F12 equals F13 equals 0.5. Now we need to find F21, and we will using the reciprocal theorem. So my F12 is 0.5. My A1 is 0.5. So I have given the relation of A2 equals A1, A2 equals to 2 by A1, which means A1 by 2A1, 0.5 by 2. So my F21 will be 0.25. So my F21 is 0.25 and my F12 is 0.5. So in this question, we use a symmetric relation. So the other example of symmetric relation is this, that we have used in the last question, where this is my surface 1, surface 2 and surface 3, and whatever the amount of radiation which is emitted from surface 1 and goes to surface 3 will be equal to the radiation emitted uh, by 1 and goes to surface 3. So in this case also my shape factor F12 will be equal to F13. So the next part is C. So again we can use the summation rule here for surface 1. And since this surface 1 is a flat surface, which means F11 is 0 and my F12 will become 1. That means the amount of radiation going out from surface 1 will all received by surface 2. The 100% of the radiation received by surface 2. So by reciprocal theorem, this is my shape factor which is 0.63, and we can also find the shape factor F22 by summation rule at surface 2. Equal to 1, and my F22 will be 1 minus F21, which is 1 minus 2 by pi. So it will be pi minus 2 by pi. So this is my shape factor F22, and my F21 is got from reciprocal theorem, which is 0.63 or 2 by pi, and my F12 is 1, which we got from the summation rule, or we can also use inspection method just to save time, seeing that this is a flat surface and therefore all the radiation coming from the surface 1 will be received by surface 2. So my part D is this. So here so this point B is at the center of surface 1, which and let me define one imaginary surface here. So this is my surface 3, this is my surface 2, this is my surface 1. Now I can again use symmetry relation here for this geometry. So using the summation rule at 1, so we can see that F11 is again 0 because it's a flat surface and the radiation will go to 3 and 2. And from the symmetry we can see that the half amount of the radiation will go to 3 and remaining half of the radiation will go to 2. So this symmetry relation valid only if there is any kind of a symmetry in the geometry, which means that F12 equal to F13. And we can put this back in the summation rule, and we can find that F12 is 0.5 and F13 is 0.5. Now we need to find the F21. So we can again use the reciprocal theorem to find the F21. And F12. So my F12 is 0.5, my A1 is 200 mm multiplied by L, and my A2 will be my 45. This is 100. So it will be 100 root 2 multiplied by L. So 100 L. So it will be 1 by root 2. So this is my F21. So my F12 is 0.5 from symmetry, and my F21 is 1 by root 2 from reciprocal theorem. So now coming back to the last case here. Let me draw here the last. So this is my surface 1. This is my surface 2. And let me draw imaginary surface here 3. Now again we can start with the summation rule at 1. So again we can use a symmetry relation, that is whatever the radiation emitted from surface 1 go to surface 3, and the same amount of radiation go to surface 2 also, which means that F12 equals F13. So I can put this in the summation rule to find F12 0.5, and F13 is also 0.5. Now we can use the reciprocal theorem to find shape factor F21. So this is infinite surface. So my area A2 is going infinity because this is an infinite surface, which means that as my area A2 goes to infinity, my shape factor F21 goes to 0 because this is my infinity. So basically it is F12A1 divided by infinity, which is F21 tends to 0, which means no amount of radiation coming from surface 2 will incident on surface 1. I mean, it is negligible. So my shape factor F21 is 10 to 0 because my area A2 is tending to infinity, because here there is a infinite surface which is given, infinite in both directions. So any doubt in this question?
No, sir.
So let's move to the next one. So a circular ice ring 25 meter in diameter is enclosed by a hemispherical dome 35 mm in diameter. If the ice and the dome surfaces may be approximated as black bodies and are at temperature 0 and 15 degrees Celsius, what is the rate of radiative transfer from dome to the ring? So we have given a ice ring and there is a dome above it. So let's say this is my surface 1 and this is my surface 2, and the air at is at temperature T infinity, which is, we have not given anything, no. So the surface 1 is at temperature 0 degrees Celsius and surface 2 is at 15 degrees Celsius. The diameter of ice rink is 25 meter and diameter of hemispherical dome is 35 meter, and we need to find the total heat transfer. So the heat transfer will be this is my heat transfer from surface 2 to surface 1, and from surface 1 there will be no heat transfer because the shape factor F11 will be 0. That means whatever the radiation coming out from the surface 1 will fall at surface 2, and there will be a exchange of the heat transfer from surface 2 to surface 1 or surface 1 to surface 2. So this is 0. So we need to find the shape factor F21. So we know something about shape factor F at surface 1. Then from the summation rule.
Excuse me, sir. Why you are taking Q11?
I'm not taking Q11. I'm just showing that it is 0 because the shape factor at F11 is 0. So I'm just
heat transfer should be from Q12.
Yeah. So it will be Q12 and all from Q21. So basically there will be a same heat transfer. So the amount of heat transfer should be same, 1, 2 or 2, 1. So my Q12 will be, okay, let me write in Q12. So here my shape factor is F12 will be 1, which means so this is 1 here because this is 0. Multiply by 5.67 10 to the power minus 8, and my temperature in Kelvin is 273.4 minus 288 to the power 4, which means when I solve this question I will get Q12 is minus 3.69 10 to the power 4 watt, which means that my heat transfer from the other side, because it is in minus, which means my Q21 will be plus 3.69 10 to the power 4 watt. So just to recap, in this question we have a two surface, one ice stream and one hemispherical dome, and we need to find the heat transfer. So we select a surface 1 as a base, and we identify the shape factor from surface 1. So the shape factor from surface 1 to itself is 0. That means the shape factor from surface 1 to surface 2 is 1. And then the total heat transfer from surface 1 is the summation of Q11 and Q12. This Q11 is 0 because shape factor is 0, and therefore the total heat transfer is just Q equals Q12. So we found the Q12 using the Stephen Boltzmann law. We found this shape factor by this summation rule, and we found the magnitude of the total heat transfer. Any doubt?
So, sir, you mean to say that this summation rule is applicable to rate of heat transfer also, that Q12 plus Q11 should also be equal to 1?
It is only applicable to find the shape factors. That's it. This Q11 and Q22, it's just a total heat transfer. That's it. It is independent of this summation rule or the reciprocal rule. From using the summation rule, we can only find the shape factors, because the shape factors only depends on the type of geometry. And depending on the geometry, we can use the symmetry property, summation rule, reciprocal rule, so on.
But you have written, sir, Q11 plus Q12 equal to 0.
This is not because of the summation rule. It is just, I have given the two surface here. Let's say this is my surface 1 and 2. Let me try a surface. So let's say this is my surface 1 and this is small surface 2. So here the heat transfer from surface 1 can be written as Q11 plus Q12, because the radiation from the surface 1 will receive surface 1 also. So there will be some no. Yeah, I should not write like this. Yeah. So basically the total radiation is just from surface Q12 or from Q21. That's it. Because this Q11, even if my shape factor F11 is not equal to 0, the surface has on the same temperature, right? Because the surface is the same temperature, which means there will be a no radiation heat transfer. Because even if there is a radiation coming out from surface 1 and incident on the surface 1 itself, the whole surface is some constant temperature Ts, which means that my heat transfer is proportional to T to the power 4 power, and this is the equal temperature, which is my heat transfer at T to surface 1 is 0, because it's at the same temperature. So basically I should write the total heat transfer is due to only surface 1 2 or surface 2 1. That's it. Yeah. So it's a bad way of writing it. Should not be written like this. Am I making sense here?
Okay, no problem, sir.
Okay. So let's move to the next question. So in this question, consider the arrangement of the three black surfaces shown, where A1 is small compared to A2 and A3. Determine the value of F13. Calculate the net radiation from A1 to A3. If A1 is 0.05 meters square, T1 and T3 are given. So we have given a surface. So this is my surface 1. This is my surface 3. This is my surface 2. And let's say this remaining surface is surface 4. So my length is 2 meter, diameter 3 meter, and it is given that A2 is much larger than A1. So we have not given anything related to the shape factor. So in this problem also we can use the empirical correlation. So using the summation rule at 1, so this is my surface 1, and we can see that the radiation at surface 1 coming out from surface 1 is not falling back, which means my F11 is equals to 0. Similarly, the radiation coming out from surface 1 will not fall back to surface 4. It will go straight in the straight direction, either to surface 3 or surface 2, which means my F14 is also 0. So my F12 plus F13 equals to 1. Now I will be using empirical correlation for two parallel surface. So that you can find in the book. So if I use that, so this is my surface 1 and this is my surface 2. So one of the empirical relation I will write here. So this is the correlation I will use. So my D diameter is 3 meter and length is 2 meter. So on solving this, so this relation you can also find in the same book in equation 13.8. So my F12 will be 0.36 by solving this correlation, and then I can use the summation rule to find F13, which is 1 minus F12. So my F13 is 0.64. Or we can also use the graph, because this is the case of two parallel discs. So we can use a graph for two parallel discs, two parallel plate also. So in for these two conditions, we can use a graph also to find the shape vector. So by using graph or correlation, we get the shape vector F12, and then from the summation rule, we get F13, which is 0.64. Then my heat transfer from surface 1 to surface 3 will be this. So my surface area of surface 1 is 0.05, F13 is 0.64, and this is my Stephen Boltzmann constant. And my temperature T1 is 1000 Kelvin, and temperature T3 is 500 Kelvin. So just calculating this, we will get heat transfer Q13 as 1700 watt. So again, this is the case of two parallel discs. So if there is a case of two parallel plates or discs, we can use the empirical correlation to find the view factor between two parallel surfaces by using the graph or empirical correlation, and then we use the summation rule or reciprocal rule to find the surface vector of other surface or the side surface. So here we don't need to find it at the top surface. So by either using summation or reciprocal theorem, we can find the other shape factor of other surfaces. Then we can use this Stephen Boltzmann law to find the heat transfer. So it's a standard problem. So any doubt in this question?
No, sir.
Okay, so let's move to the next one. So consider two very large parallel plates with diffuse gray surface. We have given temperature and emissivity of two surfaces, and we need to determine the irradiation and radiosity for the upper plate. What is the radiosity for the lower plate? What is the net radiation exchange between the plates per unit area of the plates? So we have given two plates here. This is my plate 1 and plate 2. First we need to find the irradiation to the upper plate. So the irradiation to the upper plate is defined as the radiation flux incident on surface 1 to surface from surface 2. So the radiosity at surface 1 will be just a heat radiation coming out from the surface. So my radiosity will be at surface 1 will be around 56.7 kilowatt per meter square. Then we need to find the irradiation. Now for the irradiation we have
So this J1, I think it should not be kilo. So what it should be watt.
no, it is when you calculate you will find around 56.710 to the power 3 watt per meter square. So I just write this quantity into this kilowatt 56.7.
Okay.
So to calculate the irradiation, surface 1 has temperature 1000 Kelvin, 2 is 500 Kelvin. So there will be some radiation emitted from surface 2 to surface 1, and there will be some radiation emitted from surface 1 to surface 2, and there will be a reflection from surface 2 to surface 1. So the irradiation contains two parts. First is the radiation coming from surface 2, which is this. Since surface 2 is not a black body, the emissivity is 0.8. And the other part is the reflectivity, because the emissivity of surface 2 is 0.8, which means that it will absorb some radiation, it will emit some part of the radiation, and it will reflect some part of the radiation. Whereas whatever the radiation goes to surface 1, it will absorb it. it will absorb the complete radiation because it's a black body. The emissivity here is 1. But the surface 2 is not a black body. That means the radiation, whatever the radiation coming from surface 1 will hit surface 2, and there will be a reflection also because surface 2 is not a black body. That means some part of the radiation will escape from surface 2 in the form of reflection. So the irradiation, that means the incoming radiation for surface 1 will be from surface 2 and will be from reflection from surface 2. So this rho 2 I can write as rho plus C equals 1, which means my rho 2 will be 1 minus E2. I can write the irradiation at surface 1 as E2, energy from surface 2, and energy from surface 1. So E2 is 0.8, and energy from surface 2 will be rho T to the power 4. This is 0.8. This is rho T1 to the power 4. T2 is 500. And T1 is 1000. So my irradiation, that means incoming radiation to surface 1 will be 14.17 kilowatt per meter square. So this is my incoming radiation to surface 1, and this is my outgoing radiation of surface 1. So if, let's say, consider my surface 1 is also not a black body, it has some emissivity which is less than 1. In that case, my radiosity will be the radiation emitted from surface 1 plus some reflection from surface 1. Because there will be some reflection if my surface 1 is not a black body. But since it's a black body, that means there will be no reflection from surface 1, only reflection from surface 2. Then we need to find the radiosity for lower plate. So since my lower plate is not a black body, so there will be emission. And there will be a reflectivity. So and this E2, so here it should be E1 because the reflection is coming from surface 1 here. So it is the same equation as this. So my radiosity will be equal to 14.17 kilowatt. So it's the same equation as irradiation at surface 1. And calculate the net radiation between two surfaces. My net radiation will be difference between radiosity and irradiation at surface 1, which means the radiosity at surface 1 was 56.7 and my irradiation was 14.17. which means my net radiation is 42.5 kilowatt. So we found the net radiation, which is the difference between irradiation and the radiosity. And we found the radiosity and irradiation at surface 1 and radiosity at surface 2. So any doubt here?
Sir, this transmissivity for both the cases we have taken 0.
So we have only emissivity and reflectivity. And
what about the transmissivity? Okay, transmissivity for surface 1 will be 0. But
yeah.
What about 2?
So transmissivity is required to calculate the total irradiation at surface 2. But to calculate the radiosity, we just need a reflective part and the emissive part at surface 2. We don't require the other part, right?
No. But you are taking that reflectivity J2 is like J2 you have calculated. Emissivity 2.
So my point is, let's say this is my surface and this is not a black body, which means that whatever the let's say this is my incoming irradiation at this surface. Let's say this is my surface 2 and this is my incoming radiation, and there will be some emissivity, there will be some absorption at the surface, and there will be some reflectivity. So when we calculate the radiosity, which is the total emission, this total emission is coming from the emissivity part, which is...
But there will be transmissivity also. That transmissivity should also be there.
Yeah, it should be there because it's not a black body, so it should be there at surface 2.
But we are taking it 0.
For radiosity, we don't need that. We don't need the absorption of radiation because we are calculating the outgoing radiation. It is so nothing to do with the absorption. We only need to consider the reflective.
No, I am talking about transmissivity, not absorption.
That is the same, right? I mean, the radiation, whatever the radiation will absorb, it will transmit, right?
No, sir. That alpha plus rho plus tau is 1. Not emissivity plus alpha plus rho.
You mean
alpha plus rho plus tau is...
You are considering the reflective part, not talking about the reflective part, right?
I'm talking about transmissivity.
Yeah, that it fall at the surface, then it reflect back, that part, right? This tau part.
Yes.
So that I already considered here, right? For the radiosity.
This is rho reflectivity you have considered. You have written rho 2. This is reflectivity. This is not transmissivity. Understanding that transmissivity, why we are taking it 0. Because we are having absorptivity. When there is incident radiation, then either it will be some part will be absorbed, some will be reflected, and some will be transmitted. So the transmissivity, that ratio of the fraction which is transmitted, that we are taking 0.
No, I got it. No, we are not considering 0 here. So you actually mean this part. This is the transmissivity. So this is the reflective part, and this is the uh, transmit.
No. This is the emission. This is the emission.
See, the radiosity only contains the emission and the reflective part. I don't know what part you are actually asking.
I am asking
Because your
that whatever is you are considering, whatever is irradiation from surface 1 to the surface 2, the same is reflected back.
so this is the reflection part, rho 2.
Yeah. And okay then. You have taken reflectivity and that is less than 1.
Yeah.
Okay.
So okay, then let's move to the next. So this is a true and false type of a question. So the first statement says that a body at thermodynamic temperature above zero emits radiation in all.
You make it a little bit closer because I'm not able to read. Yes. Yes.
Yeah. So the statement one says that a body at thermodynamic temperature above zero emits radiation in all direction over a wide range of wavelength. The amount of radiation energy emitted from the surface at a given wavelength depends on the material of the body and the condition of its surface as well as surface temperature. Therefore, different bodies may emit different amount of radiation per unit surface area even when they are at same temperature. So is it a correct option?
Yes, sir. It is true.
Yeah, it is a true correct option because even if the surface is at the same temperature, depending upon the property of the surface like emissivity, reflectivity, or the total absorption capacity, it can emit the different amount of radiosity or the radiation, which means this statement one is correct. So statement two is a black body is defined as a perfect emitter and absorber of a radiation at a specified temperature and wavelength. No surface can emit more energy than a black body. A black body absorbs all radiation regardless of wavelength and direction. Also, a black body emits radiation energy uniformly in all direction per unit area, normal to direction of emission, which means black body is a diffusive emitter. Is it correct?
It is true, sir.
Yeah, so black body can absorb and emit all kinds of radiation, and it's a perfect diffusive body. So both statements are correct. So here the correct option is true. So the next question is same. The first statement says that for a black body, a radiosity is different from the emissive power since a black body reflects all radiation incident on it. Is it true?
I think that is false.
Yeah, because black body can absorb all kind of radiation, so there will be no reflectivity from the black body, which means it cannot reflect back. So the rho will be zero for the black body. So this statement one is false. The second statement is the spectral intensity for emitted radiation can be defined as the rate at which radiation energy emitted at the wavelength lambda in the theta phi direction per unit area normal to its direction per unit solid angle about this direction. Is it correct?
I think it is correct. I'm not sure.
It's a correct statement. So last week we solved few problems related to this. So we calculate the intensity as the heat exchange between two surface, which is from surface I to J divided by uh, angle at surface I and cross sectional area, and I think it was a solid angle. Might be wrong formula, but the formula looks similar to this. So this is what spectral intensity is. So the second statement is correct and the first statement is wrong. So here the option B is correct answer. So let's move to the ninth one. Let's to the eighth question for now. We will come back. Eighth question is similar to the question we have solved for the previous week. Like we solved a question like this. So previously, so we have a same concept here. So we will solve this at last if we have a time. So let's move to the question number 9 here. So again, it's a true false question. So the first statement says that the total hemispherical emissivity of a surface at temperature T is equal to its total hemispherical absorptivity for radiation coming from the black body at the same temperature.
I think it is Kirchhoff's law.
Yeah, so this is the Kirchhoff's law. So this statement one is correct. So this law is valid only for the enclosed black body surfaces, which means that whatever the radiation emit from the surface, it will all reflect back and both will be equal. So the second statement is the emissivity of a surface at a specified wavelength, direction and temperature is always equal to its absorptivity at the same wavelength, direction and temperature. This is the form of Kirchhoff's law that involves no restriction. So is that correct?
I think it is spectral form of Kirchhoff's law, so it is true.
Yeah, so Kirchhoff's law can also be given in terms of spectral form, which means here my emissivity and capacity of absorption at specified wavelength and direction is equal. So this is modified Kirchhoff's law. So both are correct. So here option A, true, is the correct option. So let's move to the next one. So in this question, cryogenic fluid flow through a long tube of cryogenic fluid flow through a long tube of 20 mm diameter, the outer surface of which is diffuse and gray with emissivity of 0.02 and temperature is 77 Kelvin. This tube is concentric with a larger tube of 50 mm diameter. The inner tube surface of which is diffuse and gray with emissivity 0.05 and temperature T2 is 300 Kelvin. The space between the surface is evacuated. Calculate the heat gain by cryogenic fluid per unit length of tube. If a thin radiation of shield 35 mm diameter and epsilon 3 0.02 is inserted midway between the inner and outer surface, calculate the change in heat gain per unit length of the tube. So we have a tube here and there is the outer tube. So we need to find the heat transfer between these two surfaces, and also when we add shield surface between this tube. So we need to find the heat transfer between these two cases with or without the shield. So for a large two circular cylinder without shield, my heat transfer can be given as, so this is my surface 1 and this is my surface 2. So this is my relation for radiation heat exchange between two surfaces. This is a general relation. For two parallel circular cylinder, we can say that my A1 and A2 is.
So there should be emissivity also in the numerator.
Yeah, so this is my resistance function.
No, in the numerator there should be emissivity also.
No. So my emissivity will come in the resistance functions only. So yeah, it will become in the resistance function. Yeah. So this is my space resistance and this is my radiation heat exchange between two parallel surfaces from surface 1 and this is from surface 2. And this is the space resistance between surface 1 and surface 2. So for the long circular cylinder, we can write area A1 by A2 as R1 by R2 and my shape factor F12 will be 1 because my shape factor F11 is 0. So by summation rule, I can get F12 equals 1. So this relation gets modified to, let's say I'm multiplying and dividing by A1.
So which surface you are taking 1?
Inner surface. Yeah, inner surface. And the outer surface is 2. As of now, there is no shield in between. So this is without shield. And this is my very general relation between two parallel surfaces. It is nothing to do with the cylinder or a rectangular geometry. This is the general relation. We are deriving for the long two parallel long cylinder. So this we will get as A1 by A2. So I can modify to it will go above here. It will be D1 by D2. So this relation is for long two long parallel cylinders. For spherical surface, two parallel spherical surface, there my area A1 by A2 equals to R1 square by R2 square. So for the spherical case, we will get here squares, D1 square by D2 squares. For the long cylinder, we will get D1 by D2. And for the flat plate, long parallel flat plate, we will have the same dimension, L1 by L2. So this is my heat transfer without shield. And if using the resistance analogy, which means that This is my exchange between from 1 to 2, and this is my space resistance, and this is exchange from 2 to 1 without shield. So for without shield case, we just need to plug the values in, let's say, equation 1. So this D1L this is my temperature, and my emissivity epsilon 1 is 0.02 and epsilon 2 is 0.05. My d1 by d2 is 0.02 by 0.05. So this is my heat transfer between two surface without shield, and on calculating this I will get minus 0.5 watt per meter. So this is my heat transfer without shield. So with shield we can again use this resistance concept if we add a shield. So now consider a shield, and the shield surface is, let's say, 3. So we can use the similar resistance analogy. So my numerator will be the same because we are calculating the heat transfer from surface 1 to surface 2. That means we need to account of all the resistance between surface 1 and 2. Earlier the resistance was due to 1 2 space resistance and 2 1. Now there will be a resistance due to 1 3 space between 1 3, then space between 3 2 and 2 3, and so on. So let me write a total resistance, which is due to 1 plus the space resistance between between 1 and 3, which is 1 A1 F13, then from 3, which is twice, so I am writing twice because there is a resistance from 3 to 1 and from 3 to 2, plus space resistance between 3 and 2 plus due to 2. So this is my modified resistance. So we need to put this resistance here inside this red box here. So or we can just calculate the resistance here, and after we get the total resistance we can use just general expression here. So can calculate the total resistance. We just need to plug all the values. My emissivity of shield is 0.02. this is my emissivity 2. D2. So now by calculating this, so here my F13 equals to 1 and my F32 equals to 1 because whatever the radiation coming out from surface 1 will go to surface 3 and same with surface 3. So at the outside, whatever the radiation coming out from surface 3 will go to surface 2. So my resistance per unit length will be 1817 by L, and I just put back in this general relation. So my heat transfer with shield is minus 0.25 watt per meter. This is with shield. So my change in percent heat gain will be heat transfer with shield minus without shield divided by without shield 100%. So with shield my heat transfer is 0.25 and without shield it was 0.5. So by calculating this quantity I will get the gain of 50%, minus 50%, which is actually a loss of 50%. So just to recap, we have given a two circular cylinder and we want to find the heat transfer between two circular cylinder with or without shield. So shield is just basically another surface with a lesser magnitude of emissivity. That's all. So first we found with the two surface, that means without shield. So we use this general equation, which is valid for all kinds of geometry like parallel spheres, parallel plates, parallel cylinders, and so on. And by using this, we found the heat transfer between two parallel cylindrical surface. Then we add third cylindrical surface between two, which is a shield, and we modify this resistance, total resistance here. And then ultimately put back into the general expression with the modified resistance because now there is a three surface and we again found the heat transfer between the three surface. Then we found the total gain or total loss of heat when we add the third surface into the problem. So we found it is a loss of minus 50%. So any doubt in this problem?
No, sir.
Okay. So this problem you can try yourself for the practice. So the concept is similar to the previous week. You just need to calculate the emissivity at each part by integrating from specified lambda. And so on and it will give you the total emissive power, which is among these options. So we solved something similar problem last week. So try this for your practice. And there is a remaining one question left that we will solve in the next class. So in the next class, probably we will start with this question and then we will move to the heat exchanger problem. So that's it.
Okay, sir. Please send me the book that I have given you the mail address.
Yeah, sure.
Okay, thank you.